going to talk about the birth, the life cycles of stars, and so it starts with the birth of stars. I don't know how I got into that mode, but that was unintentional. Delete. Okay, so we've already looked, I think, at these pictures, and I'm pretty sure that in the student presentation they also showed these pictures. The way stars are born and live their lives and die is pretty similar regardless of the size, but there are some differences. So if you look here, this is for a star that is something like the size of our sun in mass. All stars form starting from a cloud of gas. We call it a molecular cloud. Now, of course, what does the term molecular mean in molecular cloud? It means that the particles are moving at a low enough speed, as they have a low enough temperature, that you can have molecules of atoms form. So they're relatively low temperature clouds. Now, when I say it's a cloud, maybe you don't know. Do you know the Latin word for cloud? Okay, it's nebula. So these planetary nebulae are clouds of gas. And when I say cloud of gas, you will tend to believe that it's similar to a cloud on Earth. But they're far, far less dense than clouds on Earth. The density, that is the number of molecules per cubic kilometer, is, I think, a number that you can count, using your hands and feet in one of these molecular clouds. There aren't that many molecules there, but that's more than you have elsewhere. So they're high density for the vacuum of space that we usually call it, but they're really, really low densities. So those molecular clouds are out there, and you have, I mentioned this, I know, before break, you have a shock wave that hits that cloud, and it makes the gas molecules, because the shock wave, they get compressed. And when they get closer, the force of gravity gets stronger, and so then gravity takes over and makes the cloud start to compress more. Max?
What are some possible sources of shock waves which cause those?
Did you ask this before?
Maybe.
So somebody asked this before. One is the death of other stars. If we look at something like a galaxy, the Milky Way galaxy, we have what we call spiral arms. And those spiral arms we tend to think is where the clouds are, and that's absolutely untrue. The spiral arms is where the shock waves are. We have shock waves that are anchored by the center of the Milky Way galaxy, which is a 3 million solar mass black hole. And then we have these shock waves that are spiraling around, and where the shock waves come, they're causing a lot of these gas clouds to then collapse and form stars. And while most of the stars that are formed are smaller stars, the bigger ones don't live very long. They give off a lot of light, and then they die and send out a shock wave. And so the shock wave that's produced by the stars that die keeps the original shock wave going. And so it self-perpetuates. How do we know this? Like everything in astronomy, how do we know this? Computer modeling. Computer modeling, and then, just like with any hypothesis, we say this is what we think happens, and then we look out and we see if we see things like that occur. And one example, a picture I'll show you later, is the Cartwheel galaxy, where you have a galaxy that another galaxy shot right through it. And so it made a shock wave go out because of the collision between the two galaxies. And that shock wave going out then causes a ring that's ever expanding of new star formation. And then you can already start to see the beginnings of spiral arms forming as well, which matches the computer models of what should happen if you were to have one galaxy shoot through the center of another. Okay, so getting back to this, one thing I should mention, most clouds will produce many, many stars. And so clusters of stars form, things like we have for lab an open cluster we have to identify. The Pleiades, Subaru, the Seven Sisters, it's an open cluster. It's a cluster of stars that all formed together at the same time. So they would have been part of one nebula, one molecular cloud, that shock wave hit, caused things to get closer, gravity took over, and stuff then condensed into clumps. And each clump became a star. And the Pleiades is what we call a poor cluster because it doesn't have, or it's an open cluster. Poor deals with galaxies like we had on the test question. But it's an open cluster because it didn't have that many stars, maybe a few hundred stars to 1,000. And so there's not that much mass, and they tend to not be as centralized and more loosely held together, which allows us to see with the naked eye because it's spread out. Okay, as the clouds collapse, everybody remembers Aldrin up here spinning and pulling his hands in because he pulled his hands in. Annual momentum is conserved, and he spun faster when he pulled it in. Well, the same happens to these clouds. You have this gas that's just randomly moving around. When it starts collapsing, you have a net rotation, and that net rotation goes faster and faster as it collapses. So then you form a system that's rotating rapidly, and just like I always think about, like a pottery class, if you just dump a lump of clay on the potter's wheel and spin the potter's wheel, it will flatten out, right? Well, that's what happens with the galaxies. It's the same physics. So they tend to flatten out. But because of magnetic fields, you also end up with what they call bipolar flows. You can see in the second picture, bipolar flows. That's charged particles that are falling in, but because of the magnetic fields caused by rotating charged particles, they get ejected along one of the two magnetic axes, or rotational axes. And so that's what the bipolar flows is, material that was being pulled in, but because of magnetic fields, it got redirected and is ejected. Then you have the stable life of the star. What kind of star is it when it's living its stable life? We have the spectral types, luminosity classes is what I meant to say, luminosity classes. Which luminosity class is it for the majority of its life, for 90% of its life? So the main sequence. So that's what's in that red box. That's the main sequence lifetime. During the main sequence lifetime, it sets up a stability between the outward force from the explosions, the inward force due to gravity. Now, as the star ages, the concentration of hydrogen in the core becomes less and less because every time you have a fusion of hydrogen to form helium, you have less hydrogen. So the ratio of hydrogen to helium changes. And that's just like in your car, changing like the air-fuel mixture in the carburetor for carbureted cars that nobody has anymore. And so it changes the efficiency of the fusion process. So the efficiency of the fusion process changes over time, which means that while on the main sequence, the stars actually behave a little bit differently depending on if they're new to the main sequence or near the end of their lives. When they get to the end of their lives, the fusion in the core really slows down because you just basically run out of fuel. And so fusion slows down, the core collapses. It gets hotter and higher pressure. And so regions outside of the core, regions where you weren't having fusion, you get high enough temperature and pressure for fusion to begin out there. And so then you have a shell of fusion around the core. So the core was where all the fusion was going on in the main sequence. But when you're in the death stage, then you have a shell outside of that starts going outward. And that goes out really quickly. So 90% of its lifetime, it was fusion in the core. 10% of its lifetime, it will have a shell burning out. And as that shell burns out, it will cause the outer portion of the star to expand rapidly. So as it expands, it cools. It's a little thermodynamics thing. So you have the gas cools. What happens to the color when something cools? It goes toward what color? It goes toward red. So when they're in the giant stage here, they expanded, hence giant. But because they expanded, they cooled, and so they're red giants. So the red giant stage is a dying stage where you have a shell that's burning outward. Now there's an interesting thing that occurs, and that is you finally can get high enough temperature and pressure in the core for helium to fuse. Now helium fusion, I have lots of slides on all these details, so I'm giving you an overview. I'm going to go quickly through the others because I really got to make up time, but the helium fusion is a little complicated. Helium plus helium gives you nothing stable. So you can't have helium fused with helium. Likewise, helium plus hydrogen gives you nothing stable. We have two stoppers in what we call the nucleosynthesis. So to have fusion of helium, you have to have three heliums all come together at the same time. Now you'll see pictures that say this helium meets this helium, and then another helium comes in. It needs to be very rapid sequence. And so we call that the triple alpha process. Why alpha? Because alpha is a shorthand way of saying a helium nucleus. So the triple alpha process is three helium nuclei coming together and forming a carbon nucleus. And so in our sun, when it's dying, when it has that shell burning out, it's going to get high enough temperature and pressure in the core for helium fusion to begin in the core. Now, once that helium fusion begins in the core, the star will return to a semblance of stability. And so when it returns to a semblance of stability, it's once again like it's back on the main sequence. But it's already a giant. It's going to stay a giant because it still has that shell burning out. Even though its core now is going to be stable, it still has the shell burning out. And so that's where we have this second stage, the one that's called the yellow giant. So the yellow giant is when you have helium fusion occurring in the core. So you have a stable core, even though you have a shell of hydrogen fusion going out. That helium fusion does not last very long. Because you have, 1/4 as much helium as you had hydrogen to begin with. And it has to have a much higher temperature for fusion to occur. It just burns much faster. And when I say burn, remember that means fusion. It's not combusting burn. When the helium is done, for a star like our sun, that's it. Now it's going to have the core collapse some more, and then you will have a shell of helium fusion that goes outward chasing the shell of hydrogen fusion. They'll both be existent at the same time. But the core is done. The core won't be able to fuse anything more. Our sun doesn't have enough mass to create the temperature and pressure necessary to fuse anything beyond helium to carbon. So what's going to happen then? We go into the second giant stage, and when we're done, when those shells reach the outer edge of the star, you're just going to have and blow a shock wave out away from the star. Now you have a lot of gas that's been pushed away as it was going through the shells burning, and then you have a shock wave that goes out through that gas, and the shock wave excites electrons in the atoms. They fall back down and they give off light. And so you have this thing that we call a planetary nebula that is gas that used to be part of the star that was blown off during its death stages, during its giant stages. Then shock wave from its death goes through that gas, makes it light up. It's called a planetary nebula only because the colors are similar to Neptune and Uranus. Has nothing to actually do with planets other than the colors are similar to colors you see in Neptune and Uranus. And at the center of that planetary nebula, you have the bones, as I like to say, that are left over of the star. So what was left over in the core? We fused hydrogen to helium, then we fused helium into what? How many alphas did it take? 3. Triple alpha process. So if you just look back there on the table, you have helium has 2 protons, right? 1, 2. If you put 3 helium together, you're going to have 2 plus 2 plus 2, 6 protons. So you count across, you see carbon is what you have with 6 protons. So the core, what's left, is primarily carbon. Now there will be some helium probably. Smaller mass stars will not be able to fuse helium, and they'll be left with a helium white dwarf rather than carbon white dwarf. There will probably be some oxygen that's produced by fusion of helium with an oxygen or with a carbon, but primarily carbon with some oxygen is what that white dwarf is. Now, Russell has asked me numerous times, none today, about how it gets so hot. It got so hot because you had gravity compacting things, making high temperatures and pressures. Then you had fusion occur. Now you've run out of fuel. You still have the high temperature and pressure. You just don't have any more reaction to undergo. And so you're just left with this very high temperature core. And so that's why the white dwarf is high temperature, because it's what's left of the core of the star. And so it's always been really hot. Now that's a really small object. How big is the planetary or the white dwarf? It might be 50 kilometers across. So basically from here to Omaha would be the diameter roughly of a white dwarf. So imagine taking something that's the mass. By this point, you've blown off a fair percentage. So let's say half of this mass of the sun, and compress it so it's a ball that fits between here and Omaha. Very dense, right? And that thing's super hot, but its area is much, much smaller than the surface area of the Earth, much less the surface area of the sun, the photosphere's surface area. So we learned that the radiation was proportional to area times temperature to the fourth power. It's a very high temperature, so that's going to raise the rate of radiation, but it's a small area, and so that lowers it. And because its area is so small, these things radiate energy, a very low percentage of their total energy each year. So they will stay hot for an extremely long time because of the total amount of thermal energy compared to how quickly they're radiating away. So over time, they will cool just because of radiation. And over the course of, let's say, somewhere 20 billion years or so, they might cool enough to fade away. And if they fade away, we call them black dwarfs. But the universe is only believed to be 13.8 billion years old, not old enough for any white dwarf to have faded away. So black dwarfs are theoretical, but are not believed to exist because it's believed the universe isn't even old enough for them to exist.
Think the universe grow up.
Yeah. Okay, so that's the life story of a star that's similar in mass to our sun. Now, one thing I have to point out, the sun may or may not form a planetary nebula. It's right on the cusp of having enough mass to actually make the planetary nebula. If the mass is a little lower, it doesn't have a big enough shock wave, and you don't have the planetary nebula. So there's some conjecture about it. When we all get to heaven, we'll find out the answer. So that's, yes, I was thinking of that in my head when I said that.
Oh, wait, what is that?
The song, yes. So that's the story for a sun-sized mass star.
Yeah, because our sun isn't large enough to become a neutron star.
That's right. So here is the same life story, but for a more massive star. With more mass, everything happens faster. Gravity is stronger, which means that it makes it pull things together faster. It makes the temperatures and pressures in the core higher, which means that it makes the fusion occur at a higher rate, so they have shorter lives. Everything is faster with more massive star. But you still start with the same thing. You have that molecular cloud, shock wave, makes it collapse. You have the bipolar flow and the disk. You have the massive star. So once again, this here is main sequence. And then when it runs out of hydrogen in the core, what's going to happen next? I'm asking you to look back at what happened with the sun. What happens when you run out of hydrogen in the core?
Doesn't it start going to its death stage?
It starts going to the death stage, and the first part of that death stage is a shell of hydrogen fusion outside of the core that rapidly burns outward. And then the core, so that makes you have a more stable situation, so kind of like a second main sequence. When the nucleus gets the right conditions and you have the helium fusion, that's when you have stability. When helium runs out, if it's a massive star, it'll start helium fusion shell, and it will start eventually fusing carbon in the core. And so it will have another thing fusing in the core. And for a massive star, it will fuse all the way up until the final stage it produces iron. And so it's going to fuse elements larger and larger and larger. So you're going to have, for each element, you start fusing the core runs out of it, you start a shell burning out, and then you start fusing the next one in the core. And so near the end, when you're in that red giant stage, the last red giant stage, you might have 5, 6 shells all burning outward at the same time of different elements. Of course, hydrogen is the outermost, then helium, then carbon, and then coming on in. So there's a lot more mass, hence a lot more energy, a lot more elements that can be fused. Why does it stop producing iron as the last stage? It stops there because iron is the most stable nucleus. Fusion was able to occur because when you take something like hydrogen and put it into helium, it's a much more stable nucleus. And hydrogen didn't have any bonds, right? It was just one thing. And so it's a much more stable nucleus, so it releases energy. But iron's the most stable. So you can fuse up to producing iron, but if you try fusion then after iron, you're going to have to absorb energy to make the fusion occur. Well, that's not going to continue on its own. That's going to die real quickly. And so what happens in these things is when you run out of, when you've gotten to iron, you have nothing that can fuse anymore. Then you have a large inward compression. And you have one of the really curious things that occur. I'm not sure if I mentioned this I know I didn't mention it today, but I'm not sure if I mentioned it in the past. With the white dwarf, the core of the white dwarf doesn't compress because you have an electron gas. Now remember, we learned from the song that the sun is a miasma of incandescent plasma. Everything from the other song, everything is a gas. Everything is completely ionized. So you have electrons, but the electrons aren't bound to any nuclei. And so when you get to the white dwarf, you have this white dwarf that's made out of, I said, carbon primarily. But they're just carbon nuclei. And then there's also electrons. And we treat these electrons as a gas. And the electrons, because of quantum physics rules, we call it degeneracy. You can't have the electrons get too close together. You probably have heard of the Pauli exclusion principle in chemistry. That's basically what we have here. So the electrons can't come together. And that's what holds up a white dwarf. It's the electron degeneracy, the fact that you can't compress the electrons any closer. Well, with the with the very massive star, once you run out of fuel and it starts compressing, you actually have forces that are so strong that you force the electrons and the nuclei together, and you essentially convert everything into neutrons. All the protons, electrons, they're smashed together and undergo particle interaction that produces neutrons. And so you very quickly take all of these elements that you've made up, iron and whatnot, and you reverse the process and bring it all back to neutrons. And then neutron degeneracy doesn't allow that to collapse. And you're left with a neutron star that's held up by neutron degeneracy. Neutron star, now we're talking a mass that's like 3 times the mass of our sun, would fit within the city limits of Lincoln. Right, so that's a huge amount of mass in a small region. The density of a neutron star is the same as the density of the nucleus of an atom. And so that's how a neutron star is produced. Obviously super hot because once again you're at the core of the star, and this is a much hotter star to begin with. Furthermore, because it's shrunk so much, these things tend to rotate super fast. And so I'll talk about pulsars, I'm not going to talk about the pulsar aspect right now. If you have the most massive star, one that's more than 4 solar masses at its depth, it actually has enough mass to force the neutrons too close together. And then, well, you know what the truth is? We don't know what happens. What we know is we force the mass so close together that it creates a region where light can't escape. We learned about the escape velocity. Something has to be traveling 11.2 kilometers per second to escape from the surface of the Earth. If you were to go to Jupiter, it have to travel a lot faster to get away. If you go to the moon, much slower to get away. Well, once you have collapsed that core that was hydrogen or helium, neutrons. Once you've collapsed that neutron core, you have so much mass in such a small region that not even light can escape. And so this was first theorized by Thomas More, way back, and he just called it a dark star. It would be dark because light couldn't escape. Now we have a much more common term for it. We call it a black hole. Black because black is what we call something when we see no light coming from it. And so it's a black hole because you look out there and there's just a hole where there's no light coming. You can't see a black hole. Now you can see things orbiting the black hole. You see around it. You can't see a black hole. So that's the other option. So that's why the last stage it says neutron star or black hole. So if it's more than 4 solar masses at its depth, it's going to be a black hole. If it's less than 4 solar masses, more than a couple solar masses, it'd be a neutron star. If it's less than 1.4 solar masses, then it will be a white dwarf. So the depth mass determines which state it's going to end up with. Maxwell.
So then how is the supernova created? It's the compression?
Okay, so the supernova is when you've used up all of your gases, you fuse things to iron, and then you have nothing more to create an outward explosion, so everything just falls in.
Okay.
And it's that inward collapse, which occurs really quickly. It causes the supernova. Now, that's one type of supernova. We'll see that there are two types. Well, there's a type 1 and a type 2 supernova. There are variations on type 1s and type 2s as well. So that's, I'd say the minute tour, but it took me 28 minutes to get that in there, of star lifetimes from start to finish. So now let's look at a little more details. So one thing to note is stars, they don't change much in our lifetimes at all. Even a supermassive star has a lifetime that's measured in millions of years. So how could we know anything about this process if it takes millions of years? And of course, the answer's up there, and you can all read it. Russell will tell us, computer modeling. Using the physics we understand and computer models, we can calculate what should happen. And then once we've made predictions about what should happen, what's the next step? You look for places where you have the conditions you predicted to see if the outcomes that you predicted are occurring there. So scientists do have a fair amount of confidence in all of this because they have computer models that, based on the science we see on Earth, predict this, and then observations that match the predictions of the computer models. Do you have a question, Max?
No.
Okay. I've talked through everything here, so I'm not going to mention that. And of course, I talked through this slide. I think I talked through everything on this slide already. Yeah, I wrote on here evolution of low mass. I should have come here to begin with. So just so we'd be clear, low mass here means masses that are no more than about 2 solar masses. There, I have a number written down. And then higher masses, ones that are more like 4-ish. The HR diagram, what was the purpose of the HR diagram? The Hertzsprung-Russell diagram, developed independently by Mr. Hertzsprung and Mr. Russell, whatever their first names were. What was the purpose? What did you use it for on the test?
Oh, to determine basically whether the size of the star and what the temperature and color and its mass as well.
Well, we actually plot the luminosity and the temperature, and what it allows us to do is to classify the stars. It's a way of classifying them and saying, okay, so we have this type of star. Main sequence is here. We have subgiants, giants, bright giants, supergiants, bright supergiants, light dwarfs. It's a way of classifying. But we can also use this then with those classifications to help us understand the life cycle of a star. So when a star starts, it's a cloud of gas. What temperature do you suppose that cloud of gas is? Just take a shot in the dark.
Hot enough to kill us.
No.
Okay. Cold enough to let us survive.
No.
Cold enough to kill us.
Yes. You knew it was going to be somewhere in there.
I mean, it's only 3 hours.
It's going to start out somewhere around 3 kelvins. Where's 3 kelvins come on this graph?
No, it's like the line at the end.
It's way out here, right?
Yeah.
So they start way out here. Are they giving off light when they're a cloud of gas? Not really. So they're really low and over to the right. But then as it starts collapsing, gravitation makes things go faster as they fall in. Going faster means higher temperature. So the temperature starts rising. As the temperature starts rising, it starts giving off light. So it starts way over on the right, but it starts coming up. So here we can see where it reaches into the frame of our HR diagram. Now, at some point, it's going to start fusion. And that's the turn-on point of the star. It's a protostar. It's a forming star until fusion begins. It can be giving off some light just because it's hot, but it doesn't make it a star because it's giving off light. Remember, even right now, Jupiter, Saturn, those planets are giving off more energy than they absorb. They're cooling down. And so, in a way, you could say it's giving off light because light's electromagnetic radiation. They're giving off electromagnetic radiation more than they're absorbing. But you really don't see much until fusion begins. When fusion begins, then you have suddenly an outward pressure. Before that, it was all just gravity crushing things in. When fusion begins, now you have an outward force, and it starts clearing the atmosphere around it. When you clear the atmosphere around it, then you start to see the star. So the key of going from a protostar to a star is when fusion begins. And honestly, I don't know exactly where in the diagram fusion is going to begin, but I think in this diagram it's going to be somewhere right about there. So there fusion begins and it's a star. Once the fusion begins, it's quickly going to move into a stable, hydrostatic equilibrium where the outward force matches the inward force. And it's going to match that or reach that stability here. So that is the beginning. One end? Two? Okay. I used to be good at spelling back when I was in high school. The older I've gotten, the worse I've become, which makes no sense to me. I think it has to do with having less confidence and starting to doubt myself and say, it can't be the thing that seemed obvious. So there's the beginning of the main sequence is down at the lower left-hand portion of the main sequence. And then as it lives its life, it starts moving up and to the right. What does it mean if it's moving to the right? It's getting cooler. So as a star lives on the main sequence, it slowly gets cooler. But it's also moving up, which means it's being more luminous. How can it be more luminous and cooler? It's getting bigger. So as the star works its way through the main sequence, let me change color. As it works its way through the main sequence, it's slowly getting cooler but larger. And that all has to do with the rate at which fusion is occurring in the core. So when it gets out there to where my green arrow is, that's when the core really starts slowing down. When the core slows down, what happens? You have a shell of hydrogen fusion that goes outward. And that shell of hydrogen fusion is what causes it to go into the giant stage. So it's hydrogen fusion. Actually, I should change color again, shouldn't I? So out here we have the hydrogen shell. And then right at the tip, this is where helium fusion begins. When helium fusion begins, it dies back down for its essentially second main sequence term. But now it's not on the main sequence, it's up there in the giant region. And then, what do you suppose happens I'm truly running out of colors here. What do you suppose happens right there? Yeah. The helium core stops, but you have the helium shell begins. Not much difference in those two colors, is there? And finally, I've pretty much used all the colors available to me. What happened right there? That's the end of fusion. At that point, you have the collapse down, shockwave going out, making the planetary nebula. The light you see as it's going over to the left now is the light that's produced by the planetary nebula and the white dwarf as you start to see that white dwarf. And then it comes down here, and you have it ending up in the white dwarfs section. So it'll start up here as a white dwarf and work its way down this way over time, eventually cooling enough to become a black dwarf. So the HR diagram can be thought of as a time sequence mapping. You can see how something is going to change over time. Now, it depends on its mass. I followed out the yellow path, which was a mass similar to our sun. But there's also the blue path. Blue path comes in pretty similar to the yellow path, but it has a lot more mass, and because it has a lot more mass, it has more luminosity, and it gets to a much higher temperature. You're still going to have the same basic aspects of fusion will begin somewhere around here, starts on the main sequence here, works its way up through the main sequence until about there, and then it goes off into its giant stages. And so you have, a beginning of fusion of something else in the core. After that, you can have zigs like that, but it goes quicker and quicker and quicker, so you don't really see the action here until you have the supernova. So the HR diagram helps us to not only categorize stars, but allows us to visualize how the stars are going to progress through their lifetimes. First clicker question. How do scientists know that the life sequence of a star is what was shown on the preceding graphs? Yes, 33.
Who's ready for the lab final?
I am. You have your clicker, Russell?
You guys are so confident.
Okay, we had 1, 3, and 6. Max, tell the class which one you chose and why.
I actually chose A because we talked about how we can't live to see the whole lifespan, but the scientists kind of think that they know because of the laws of physics, and so they haven't proven it, or they haven't seen it, but based on the theory of the laws, they think it must be true.
Okay, good explanation. He was a lone wolf on that one. Red is not going to work for this. What would you say to the 3 people who answered B, Max?
Because the laboratory, you can't produce a star in a laboratory, and
Can't produce a star in a laboratory. That couldn't have been the answer. C, because they have tested the predictions of hypothesis theory and found confirmation of hypothesis theory. Is that true? Based on the words I said, is that true?
Yes.
Yes, it is. So either one of these are reasonable. C is the one that really fits with the scientific method, right? That is, you have to not just say, oh, it's a beautiful hypothesis, right? That was Aristotle's way. It's a beautiful hypothesis. It must be true. But the measurements, which in this case, the best we can do is understanding the physics on Earth and then using computer modeling to figure out what should be happening and then looking for places where the predictions occur. And so they do that, but there is always that temptation to say, well, the theory seems pretty good to me. I've been indoctrinated. I'm going to believe it. So I am okay with your answer, Max. But C would be the correct scientific answer. The correct scientific and the actual don't always correspond. All right. Now getting down to the beginning part. Protostar is the term we give to a future star, something that is developing. So we have the beginning parts that I've talked about of gas cloud that starts condensing because of conservation of angular momentum. It flattens out into a disk, and you have those bipolar flows with the protostar at its center. That is the big clump of mass at the center. Here is the actual numbers. 7 to 15 kelvins is the temperature. And okay, I was wrong on the densities, 100 to 300 molecules per cubic centimeter. I said per cubic kilometer. Clearly, I was grossly wrong. But still, it's very low density compared to anything that we would have on Earth. And notice the mass. These molecular clouds might be 10,000 solar masses or more. That is, it can produce 10,000 stars the size of our sun. Excuse me. I hate when that happens. Thank you. Thank you very much. Have you guys ever seen this picture? Yes? No? Yeah. This picture was taken soon after I became a college professor. And these are part of the Eagle Nebula. I think they call it the Pillars of Creation. And what's going on in this picture is actually really interesting. First of all, size. I don't have size shown on here, but these things are like 5 light years tall. Right? So this is really big. And if you look at it, you see some really cool features. Like, what in the world is that? What in the world is, oh, come on, that? Those are predictions from the computer modeling of what should happen when stars form. These big columns of gas are molecular cloud that a shock wave has hit and is causing it to collapse. And you form these regions with high density, and those regions with high density kind of stay put as the rest of the cloud continues to collapse. And so they get left out. And so those things, they call them eggs because it's the Eagle Nebula. They're the eggs in the Eagle. They're evaporating gaseous globules. Eggs. What does that mean? Those are what we believe are protostars. Protostars that the rest of the nebula has pulled away from it, and you're left with that protostar that will soon become a star. Now, I say will soon. This is obviously a long distance away. So they surely have already formed full-on stars, may have even already died, because they're so far away that we see the picture long after the light was sent. So we're looking back in time when we look back at a picture like this, and we're seeing star formation occurring in this picture. And so if you look around, you'll see there's other places where you have things like those all over the place. So this was a really exciting picture for astronomers because it was a picture showing lots of star formation in the process. And last thing, infrared telescopes can detect the protostars inside of those little eggs.
Aww. Little babies.
Yes, yes. Here's some pretty pictures of protostars. I could look at these all day and still not know what I'm looking at. What you have is essentially the center, the bright dot, That's where you have the clump of mass that will become a star. And then the dark region around it is a bunch of gas that's enclosing it, keeping light from coming out. This picture here, to me, looks like one of those things in Star Wars, when they come into the Death Star. But this is a bipolar flow. You have one flow going this way, one flow going this way. And one of the telltale things about these bipolar flows is this thing here. That's the shock wave where the bipolar, that flow, the jet has hit gas. And so the jet's hitting the gas and it's causing a shock wave going through the gas. Now, they can use Doppler shifts to measure speeds and whatnot, so they have an idea of how fast the jets are actually traveling. And this is another prediction of the models for stellar birth that is then observed. Notice the temperature. Once a protostar heats to about 1,000,000 kelvins, some nuclear fusion begins. How hot is the core of our star?
It was like,
15 to 16 million kelvins. So that's actually a lot cooler than the temperature in the core of our star. So that's just a little beginning. It's kind of sputtering. It's not really, the full-fledged kind of fusion that we have now. This is showing birth lines. The red dashes are the paths on the HR diagram for stars of different masses as they're going from protostar to star. What do they all have in common? They all have in common that fusion, now this one here, where the dashed line becomes a solid line, should be the point where fusion in the core begins, where it goes from being a protostar to a star. And so you have, the line where it goes from being a protostar to a star is roughly what I just drew. And you see that the trajectory changes after that. And notice the times. The white dashes tell us time. So something that's like the mass of our sun is going to take in the ballpark of 10 million years to be birthed. It doesn't happen overnight. Now, this is the scientific understanding. Once they start throwing around times like 10 million years or 13.8 billion years, there's a lot of consternation because according to a traditional interpretation of the Bible using Ussher's chronology, we have an age for when the creation of life on Earth occurred of roughly 6,000 years ago. And there are some people who say, not only is that interpretation a correct and truthful interpretation, but the entire universe was created at the same time that life on Earth was created, so the entire universe is only 6,000 years old. So at this point, we start to come to some conflict between our religious beliefs and our scientific beliefs. Now, you don't have to have that religious belief and be a Seventh-day Adventist. Seventh-day Adventists cover the gamut. I've talked to people in the GC, Umberto Rossi specifically, about my belief system and how that fits with the church. He said that's perfectly in accordance. My belief is that the Earth or the universe is indeed 13.8 billion years old. That God created the laws of physics and He put the energy and formed the universe, and then the universe developed as dictated by His laws. And then at a later time, He came in and created life on this earth. So to me, I see no conflict between my religious belief and the scientific belief here. If you do, that's fine. I'm not here to indoctrinate you. You do need to know what the scientific understanding is, but you don't have to say, and that's what I adopt. I want to make sure it's clear that we're not trying to indoctrinate you into something. Just make sure you understand what the science is and why they have it. So we're out of time, so I will stop here.